So this is the sixth session on signals and systems, and what we are going to do is to study how to write MATLAB programs for generating a discrete unit step, how to generate discrete unit ramp and discrete impulse signals, and also we'll study how to write the program for piecewise linear functions. That is what we are going to do. All right, so let us start. Now, before looking at those functions and the calling functions, calling programs, let me explain to you two of the important commands in MATLAB called as zeros and ones functions. If you remember details from some of the previous lectures, you will note that the step signal we studied in the continuous type of step signal, and we saw that it was either 0 or 1. Similarly, a discrete unit step also will be either 0 or 1, and this can be easily implemented. That is one way of doing it, is to use zeros and ones functions. So we first study them. All right. So one possible zeros command that you can write is zeros 1 comma 4. So this one means this is one row. And in most of our programs, this is going to be 1 because we just want to generate a vector, one dimensional array. This number depends on how many zeros we want to generate. So if I say zeros 1 comma 4, I am generating one row of 4 zeros. If I make it 5, it will be one row of 5 zeros and so on. So if you put this command in the console and execute it, then this is what you will get: 1, 2, 3, 4. So it simply depends on what number you write here. And similar syntax is there for ones also. So if you execute a command like ones 1 followed by 6, this is what you will get. So 1, 2, 3, 4, 5, 6 ones that you get. And if you want less or more, you have to change this number. All right. Having studied zeros and ones functions, what we are going to do now is to see how they are applied in the generation of discrete step, discrete impulse, and so on. So first of all, let us look at our discrete unit step signal. This is analogous to the continuous unit step signal that we had studied, but now our time axis is discrete. So actually, the definition of the unit step signal would be that right from minus infinity up to you reach 0, it remains 0. At 0 it jumps to 1, and thereafter for every value the index. Remember, in this case our n is a discrete variable, so it will be 0, 1, 2, 3, etc. But when we actually write a program, obviously we cannot have infinite values. So there will be some range that we will be selecting. So this can be from, let's say, minus 10 to plus 10. Depending on the application, it might be convenient to choose a particular range. So you might choose, say, minus 20 to plus 20 and so on. All right. So what we want to do now is to study the function that will generate the discrete unit step given the value of n. I'll explain what that n is. So discrete step function. So function ns equal to ds. ds for discrete step. Of course, it's going to be a unit step, but I have just written in short ds. So what is the variable? What are the input variables to this function? That is capital N, just one value that you are supplying. Why that is enough? Because suppose n is 10, then it means that we are generating the unit step right from minus 10 up to plus 10. If you supply 5 here, it will mean that we are generating from minus 5 to plus 5. So just one value can be passed as an input variable to this function. What are the output? The outputs are arrays. One is the sample index, that is n, and it will start from minus n and go all the way up to plus n with an increment of 1. That is what this will be. And the corresponding values, sample values. So from minus n up to minus 1, this will have 0 values, and then from 0 onwards it will have 1s. So we need to generate the zeros and ones separately and then concatenate them. So let's look at the program now. So n1 is minus n to minus 1. Why this particular range? Because in this range we want all zeros. After that the value changes. That is why we are defining this range n1 equal to minus n to minus 1. Then we need to know how many zeros we want to insert. Therefore, you must find the length of n1. So n1 is the length of n1. And now you generate your zeros and put them in one part of the output, that is S1. So that is zeros 1 comma n1. One part, because the second part will contain all ones. All right. So what is the next array for n? So that is your n2, and it starts from 0. Note that this is ending on minus 1. Now the discrete step, as you go from minus 1 plus 1, you will get 0. So from here, as you increment by 1, you get 0, and you go all the way up to n. So that is your second array for n. Then you find the length of this and put as many ones in the second segment for S. So S2 is equal to ones 1 and 2. So you have generated your n1, you have generated your n2, S1, S2. So now you just concatenate them. So n is n1, n2, and S is S1, n2, and this is where your function ends. So it will accept n as the input and will generate two arrays, one for the sample values n, sample values S, and the other is the time discrete variable, that is n. Okay. Let us now see how this is going to be used. So let us see the calling program or the main program for calling this function. So as usual, you clear console, you clear the previous variables which are in the memory, clear figure. Then n equal to 10. This is the input, single input we have seen, we have to provide to that function. If you want to plot this from say minus 5 to plus 5, you will have to supply 5 here, and so on. So now we call the function, that is your discrete step function, and then obtain the outputs in n and s. So now all we have to do is to plot. So stem ns and all the corresponding statements that go with the graph. So grid on, etc., which we have already discussed, so I will not discuss this again. And when you enter and execute this program, this is what you will get, and this is what you expected. So from minus 10 up to minus 1, it remains 0, and from 0 up to 10, it is equal to 1. So this is your discrete unit step function. So we have studied the function for generating this, and we have studied the calling program which will generate this. All right. Next, we want discrete ramp. So discrete ramp also, the total time period you provide. So you'll provide the value of capital N, and it will generate the entire values from minus n to plus n. So it is somewhat similar, except that, so all right, so this is the before I go to the program, let me first of all explain to you what the discrete ramp is. So here I have chosen n equal to 6. So from minus 6 up to minus 1, this is going to be 0. After that, it increases with a unit slope. Now unit slope means every increment will be equal to 1 itself, because increment on the time axis itself is 1. So unit slope will be 1. When this is equal to 1, the amplitude also must be 1, so that your slope is unity. So this is how the discrete ramp with a unit slope. So this is actually a discrete unit ramp. I have written in short here, discrete ramp. Okay, this is what we want to generate. So now we study how to write the function for generating the discrete ramp. So it is again similar, but in this case our n1 part is similar. It remains all zeros, but n2 is now slightly different. In the case of unit step function, all the following values were ones, but in this case they are directly equal to n2 because this is a unit ramp. So every value of the output is equal to the sample index itself. So you can write S2 equal to N2. First generate N2 vector, N2 is equal to 0 comma N, and then S2 is equal to N2. So you have your both segments N1, N2, you concatenate them, so you get N. Then you have segments S1, S2, you concatenate them, and this is where the function ends. So now we would see how to write the calling program for this. That is straightforward. N equal to 6, and that is a value that you need to supply. So it will go from -6 to +6. These are the outputs. So the rest of the statements that are required are just for plot, because you already have them. And how to plot, how to label, etc. we already studied. So I'm not going through this again. But when you enter this program and execute it, this is what you will get. So right from -6 up to N equal to 0, this is 0. After that it increases linearly. Of course, when N is equal to 0, again it is 0 itself, because S2 is equal to N2 itself. So when N2 is 0, this is going to be 0. But then it increases with a unit slope. So this is how you generate the discrete unit ramp. Then discrete impulse. So what is the definition of the discrete impulse? So it again, theoretically, it goes from -infinity to +infinity. But then in MATLAB simulation, we can have only finite range. So I'm showing it, let's say, from -6 to +6. Now to generate the discrete impulse, when you're writing that function, you have to segment N and S both in 3 parts. So right from -6 to -1, this remains 0. Then at N equal to 0, it is 1. And for all other values of N, it is 0 again. So this is one segment, this is the second segment, and this is the third segment. See, in our previous programs, remember that we had only 2 segments, but discrete impulse will require 3 segments. And this is the definition of the discrete impulse. Incidentally, note that we have not yet studied the impulse function in the continuous time domain. It is slightly more complex, so we'll study that in some detail later on. But right now discrete impulse is comparatively straightforward, because its value simply jumps to 1 and thereafter it becomes 0. So it's easy to simulate this. The continuous time impulse is somewhat more involved. We'll study that later. All right. So how do you write the function for this? So as I said, the details are similar, except that you now need to split this into 3 segments. So N1 again -N to -1. Again find the length of this, generate your zeros. But now at N2 equal to 0, you want your value to be equal to 1. So that you specifically generate N2 equal to 0, S2 equal to 1. But thereafter, for all values of N starting from 1 to N, again you want zeros. So you define N3 from 1 to N, find its length, generate zeros. Once you have done this, then you have got all segments for N1, N1, N2, N3, all segments for S1, S1, S2, S3. You concatenate them and you got your output here. So that is returned. So what about the calling function now? The calling program is again similar, so I'm not explaining it. All you have to do is now only change the name of the calling program. The rest of the things are similar to what we have done previously. So this is discrete impulse and you provide N, so N equal to 6. And display S just for checking. So I had written that, is not really necessary for plotting. But just to check that the program was working properly, I had said display S. Then you plot this. So you require a stem command, grid on, X label, Y label, and so on. So that is standard. And when you enter this program and execute it, this is what you expect and this is what you will get. Okay. So that was about generating the discrete unit impulse.